some years back, Curiosity, I think it was, yeah, it was Curiosity was landing. And if you know anything about it, Sandy will talk about this here in a moment as well, but when the landers come down, there is this 7 minutes of darkness where you can't get any communications out of the landers. And on top of that, you get the 14 minutes of not being able to, of delay in time. And the lander's coming down, and somebody tweeted, I wonder how they do the networking on that. I don't think it's TCP/IP. I got to figure out who that person was. But anyway, I saw that, and I went, oh, that's kind of interesting. We should try to figure that out. So I called a friend of mine who works at the Jet Propulsion Laboratory, which is in Pasadena, which is, as Greg Nagel will tell you, maybe a little bit far on a weekday morning to drive, but is about an hour and a half from here or so. And I said, do you know anybody that could talk about this stuff? He says, well, I know this guy. And poor Sandy has had to endure me ever since. And so Sandy came and did a talk called Interplanetary Communication Curiosity Style in 2012 at MacTech Conference. Mm-hmm. And I think you've been to almost every one since then at that point in time. And Sandy has this really, really incredible job of being able to play with this, with space and technology and networking and whatnot. His actual title is End-to-End Information System Engineering. Now, if you know anything about JPL or NASA, that's not his title. It's got to be an acronym, so it's an EEIS. Which really, you know, his job comes down to making sure that systems are from one end to the other, talking to each other and making sure that they're working. And you know, there's a lot about protocols and formats and definitions and things like that. In the end, he's basically a JPL computer therapist and making them all get along. At least that's my version of what's going on.
Pretty close.
Sandy, so with this, we asked Sandy to talk a little bit about a couple of things in here. One of it is just sort of about insight and what they're doing today, but also from our point of view, they have to think through problems all the way through. They have to make sure they've got it nailed because they don't get to do a patch in the middle of a landing, or it just doesn't work that way. So without further ado, how about a very warm welcome for Sandy Krasner, who's going to talk about insight.
Thank you. Okay, as Neil said, I've been to almost all the MacTech conferences since the first talk I gave, except last year. Last year I was too busy landing this thing. So I'm going to tell you a little bit about what's been going on with the InSight lander. We landed the Monday after Thanksgiving. And that's sort of the first part of the presentation, and then I'm going to talk about what's going on with our next Mars lander, which is right now called Mars 2020. We'll be launching in July. And there's sort of a connection and a theme between the two of them about trying to land on Mars more and more accurately to get to the interesting stuff as quickly as we can. Okay, so this is about the InSight mission, and what we're trying to do with InSight is we're trying to understand what the inside of Mars is like. So this is the first time we've ever taken a look at the inside of one of the rocky planets. We know a fair amount about what the inside of the Earth looks like. We're trying to go find out what the inside of Mars looks like. Compare that to what we know about Earth. It helps us understand how the planets form, that type of thing. So what we're trying to do is we're trying to understand what the interior of Mars is like. And particularly, there's a set of rocky planets, Mercury, Venus, Earth, Mars. Earth has been so active over that entire time that a lot of the history of how the planets formed has been wiped out. We think Mars is probably frozen out at a somewhat earlier stage. So we're trying to figure out how do we look inside Mars. And what we're doing is there's kind of three things we're looking for. One of them is we're looking for essentially Mars quakes. And that's on Earth, that's the way we understand what the interior of the Earth is. Nobody's actually drilled down more than a mile or two into the Earth. So how do we know that we have a molten core and a crust and a mantle and a crust and convection and all that stuff? And the way they've figured that out is by measuring earthquakes. So what we've done is we put a seismometer down on Mars, and we've actually are seeing Mars quakes. So we're trying to understand that. We're trying to understand how much heat is coming out of the interior of Mars, and that'll tell us how much heat is trapped inside the planet from the way the planet's originally formed, and it's essentially that, how much heat is still inside the planet, and that tells us something about how it formed and how the structure is. And then one of the things we're trying to see is if Mars is wobbling. So if you have a, the classic thing, if you take a raw egg and spin it, it will wobble because the stuff inside is liquid. If Mars has a molten core, it will do the same type of thing on a much smaller scale. So we have a radio science experiment. We send radio waves up from the ground, the spacecraft receives them and turns back around to the Earth. We can do very sensitive Doppler experiments, and we can actually see how Mars is wobbling. My understanding is they don't really have results from that. Given all the different geometries, it takes about 2 years before we'll get that information. But they're in the process of doing that. Okay? So this will give you some idea. Well, how do we, on Earth, we've got seismometers all over the planet. How do we do this with one seismometer sitting at one point? What this is a simulation that if we have a quake or an impact that starts at one point, the waves from the quake kind of propagate through Mars, through different surface materials at different speeds. There's different polarizations and different types of waves, and they all kind of make this complex pattern. And if you think about sitting at one point on the surface here, and essentially we can sit and we can watch those waves go by and essentially reconstruct some information about where it was and what kind of structure, what kind of materials it went through. So by building up a whole series of earthquakes over some long period of time, we'll be able to get a picture of what the interior of Mars looks like. And we're actually doing that right now. So I'll show you a picture of that. Okay. This is our spacecraft as it's sitting in the assembly facility. I'm not going to go through this right now, but I will. And this is what we get to dress up as. Since I do software stuff, I don't really need to be in the clean room. The people who do the assembly do. I've actually got one picture I can show anybody afterwards if you want of me in my bunny suit in front of the spacecraft, which is just neat because how often do you get to get a picture of something that's sitting on Mars, with something that's sitting on Mars now? Okay, so our payloads. First thing I'll show you, we have two cameras. One of them is mounted under the deck of the spacecraft, and I'll show you the picture that we got immediately about 5 minutes after we landed. That was the first thing we saw from our landing site. We also have a mechanical arm that has a camera mounted on it. So the first thing we did was take the arm and scan out to see what the workspace in front of us would look like, and then we use a grapple on the arm to pick the instruments up and put them down in the right place. And then essentially, once we have the seismometer down on and the heat flow experiment that I'll talk about down on the surface, we just sit and wait and collect data. We're just waiting for quakes to happen. That sounds easy. That actually took us about 3 months to do because, NASA, we've only got one chance to do this. We want to make sure we put the stuff down in the right place, exactly where we want it, and the cables all work and all that type of thing. So this is a picture of what our seismometer looks like sitting on the surface of Mars right now. And over the top of that, there's this sort of white wok-looking thing that is a wind and thermal shield. The seismometer is so sensitive, they say they can measure deflections of the surface on the order of the size of a hydrogen atom. And unfortunately, so we can measure relatively small quakes, but also means it's really good at measuring wind blowing on the seismometer and atmospheric pressure and stuff like that. So we have a wind and pressure and thermal shield. We also have a full atmosphere station, a weather station, that tells us essentially if we're seeing seismic signals, seeing things on the seismometer, are we seeing real seismic signals or are we just seeing weather? One of the byproducts of this, though, is we got a much better understanding of weather on Mars, which was kind of not what the original idea was, but every time you take a new sensor to a new planet, you learn something new. Okay? Our deployment camera, this is our grapple for picking the instruments up. These are the two X-band antennas that receive signals from the Earth, turn around and send them back to the ground, and that's how we measure the wobble of the planet. I think I'm cheating people over on this side. Okay. All right, this is our seismometer package. So there's actually a package of very sensitive seismometers. There's a little leveling system on it so that however we put it down on the ground, we can make sure that it's perfectly level. Go back. One more. there's a little thermal blanket enclosure, and then this is the wind and thermal shield with a little skirt around the bottom so the wind can't blow up underneath it. Okay. The next one we have is our heat flow experiment, and what this is, and I think that you'll see this on the video in the next part. It's a little probe, and it hammers its way down to the ground. Let me show this, see if this will, anybody show, how do I play this? Okay. I think this is, I hope this.
Oh, thought I had reason to attack, but no.
I don't know what that is. Somebody. Anyway, what this should be is there's a video. This is a little sort of large pencil-shaped thing. It has a little motor in it, a cam. It drives around and it's supposed to, basically they call it a self-hammering nail. It's supposed to drive itself into the ground, just kind of, and it literally sounds like when they run it in the test, it tick, 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 tick. It goes about 1 millimeter every time we do that. So this is supposed to be driving down into the surface of Mars. It drags a tether behind it that has a bunch of temperature sensors on it, so we can measure what the temperature is of the ground as we go down, and we can measure how much heat is coming up out of the planet. It's supposed to go down about 15 feet. Right now it's down about 1 foot. And it seems to have gone down into the ground, possibly hit a rock, sort of rotated about 15 degrees, and then stuck. But we think, and I'll show you this at the end of the presentation, we think we actually we may have figured out a way to get it going again. So they've actually started hammering with it again, and it looks like it's starting to move. So, all right. This is our auxiliary payload sensor subsystem. This is our weather system. So we have a wind sensor, a magnetometer, because one of the things, the seismometer actually is sensitive to magnetic fields. Mars doesn't have a global magnetic field, which tells us something about the core. On the Earth, the magnetic field is formed by circulation within the core. Mars doesn't have a global magnetic field, but there are some fields, and there's actually some fields that come from the spacecraft. One of the interesting things that they've kind of discovered as a byproduct of having this is they're actually seeing magnetic pulsations that usually happen about midnight. And they think that's probably has something to do with the solar wind blowing around the planet and it's essentially forming some sort of a magnetic field that is disconnecting. So something from the tail of the magnetic field blowing down. Again, one of these serendipitous things, this isn't what they were looking for, but it's an interesting piece of information. So wind sensor, the magnetometer, we have a pressure sensor, and so all this put together gives us essentially a weather station, and we can understand what is happening there's actually a Mars Weather Service if you want to go look and find out what the temperature and the wind is like. This is buttoning up for launch. I'm going to kind of rush through this. This is the launch from Vandenberg. This is the first time we launched from the West Coast. I was in the control room on console for the launch. I was kind of bummed because I couldn't go up to the launch site. If any of you have been up to Santa Barbara or Vandenberg, turns out that the launch was completely clouded in and nobody saw anything. But in Pasadena, this is 4 in the morning, as soon as the rocket lifted off and cleared the pad, we all ran out on the plaza and we could actually see this little red spark kind of arcing across the spacecraft. So we got to see that thing heading out towards Mars. That was fun. All right. And then as we came in for landing, one of the things that Neil was talking about for EDL landing, I was in charge of making sure that all the data that was coming in from all our different spacecraft was all coming in to our stations on the ground and getting up on our screens. So when you see people sitting and watching the screens during turns out to be 5.5 minutes of terror, my job was to make sure that data was on the screen so they could see it. So that was fun. That was an exciting day. So as we're coming in, we have the InSight spacecraft is here. We have these 2 little CubeSat spacecraft. So I don't know if anybody here has had contact with CubeSats. Literally, the whole spacecraft is about the size of a shoebox. This is something they're doing a lot of colleges and that type of thing. It's almost like you had a spacecraft assembled from Radio Shack. I mean, they're very, they're cheap. They're not the type of high reliability stuff that we build, but they're easy to build, and you can build a lot of them. So one of our interesting experiments was these Marco CubeSats, and these things were actually what gave us our real-time data, so we were able to watch this as it was landing. We also had the MRO spacecraft flying over us, capturing data, and then we had 2 radio telescopes sitting on the ground as we were monitoring this. So this is our CubeSat. This is actually one of the flight spacecraft, so this isn't a model. I mean, that's the real thing. That's how big they are. This is the first time we'd ever flown one beyond the moon, so our first deep space CubeSats. It even carried a camera, and they were able to get a picture of Mars as they were flying by. And again, I'm not sure the characteristics of the camera, but I don't think it's much more than a GoPro camera. So there's lots of stuff you can do with basically commercial electronics now. I think I'm going to skip past this just because it's not so interesting. Hang on for a sec. So this was the video of us during the landing. It actually turned out to be 5 minutes and 49 seconds. This is the fastest landing we've ever done on Mars. We had some unexpected interactions with the atmosphere, and we came down a little bit faster than we expected to. That's me. And actually, that idea of how we interacted with the atmosphere relates to the second part of the presentation that I'm going to talk about terrain relative navigation. So this is us coming down our final stage. We come in on a heat shield, deploy the parachute, and then finally come down on rockets. Neil will tell you, I'm I'm very close to crying as this is going on, trying to focus. And Chris Bruvald is the guy sitting next to me is our telecommunications expert. So one of the neat things, you can see him, what's going on? Anyway. This is Gene and Brooke doing the touchdown dance. So, okay. This is the first thing we saw when we landed. Not exactly. This is the first thing we saw when we landed. Interestingly enough, we don't want to land on rocks. The first thing we see is there's this little bitty rock sitting right next to our footpads. Wouldn't have been a problem if we'd hit it, but it was kind of a surprise. There's lots of dirt kicked up on the lens, but that eventually starts to go away, and we're eventually able to see it. The other thing that was fascinating was particularly, I wasn't sitting in the room with the scientists, but apparently all the scientists on the project jumped up and leaped to the screen and started saying, all right, we're going to land here, we're going to land here, and essentially immediately started, from this one picture with all the junk on it, started picking out where we were going to put the instruments down. So that's fun. That says you're on the surface and everything's working. Okay. What I want to talk about and getting into the next topic is what does it take to find a place you can land on Mars? So for our particular mission, since we were basically just want to listen to what's going on inside the planet, it doesn't really matter exactly where we land. We can land anywhere. We're not trying to land on a particular target. So the guy who does our landing site selection, he wanted to find a place that was flat, dull, and boring. So he calls it Mars, Kansas. And we want to land someplace where we guarantee we're not going to come down on a rock, we're not going to come down in a crater, something like that. And there was particular types of soil that we need to land in that we think the probe will be able to penetrate. So they do all this survey from Mars orbit with these detailed pictures and try to guess what the terrain is like, and they eventually end up picking an area about 300 kilometers from the Curiosity, interestingly enough. And that's where we're going to come down. We need to be near the equator so we can get as much solar power as we can. We need to be at as low an altitude as possible so when we land, we have as much time on the parachute to show us down as possible and all that type of thing. So we got the whole planet to select, and we end up landing almost on top of Curiosity. What they do for these is they pick a landing site ellipse, and this is basically the area that we could land in. For our particular lander, we control where we're going to be at the top of the atmosphere. We don't actively control as we're going through the atmosphere. The 2020 landers I'll talk about can actively steer as they're going through. Since we're not real concerned about exactly where we land, we didn't do that. But this is a, let me go back. This is a 90-kilometer ellipse, or 90 or 100-kilometer ellipse, and that's our 3 sigma ellipse. So we've got a 99% chance of landing in there, which is something like if you say, oh, I want to land in downtown LA, and all I can say is I'm going to land somewhere in the LA basin. That's about the level of our accuracy. We actually ended up coming down this area about 12 kilometers off of the center of our landing ellipse. And a lot of that was due to, we just, as we were coming through the atmosphere, there were some unexpected things happening with the atmosphere and the way we flew through it, and we didn't land exactly where we expected. But again, the whole process we'd gone through said, yeah, we think we'll be safe if we land anywhere in that area. Okay. This will become, if you kind of think about this, this will become important as I start talking about strategies we have to make those landing ellipses much smaller and to be able to land almost on a dime. Okay? One of the neat things about the whole system that NASA has at Mars is we have this whole system of orbiters and everything else. So a few hours after we landed, the Mars Reconnaissance orbiter was able to fly over and actually give us pictures of where we were landing, so we could see exactly where we came down. We can see the lander. Around the lander site, we can actually see, try to come over some. We can actually see places where we've kicked up the dust. You can see kind of almost like a burn scar, or a little bit of areas where we've blown the dust off. We can see where our parachute landed and it's still got its back shell attached, and we can see where we kicked the heat shield off as we came back. So just, and again, show us that we're on Mars and everything seems to be working fine. Okay. And actually, they got a picture later when we finally got our seismometer down on the ground. It's got this big white bowl on it, so we can actually see where the seismometer is. Again, doesn't tell us much scientific, but it's kind of neat to be able to get selfies of where you are. This is our landing site. As I say, it's flat, dull, and boring, which is kind of exactly what we were looking for. There's a whole video about how we landed. I think I'm going to skip those. But these are some of the interesting things about operating things 100 million miles away. We have this tether that goes out to the instrument, the seismometer that carries all our electronic signals. The thing was so sensitive that they were worried that as the cable expanded and contracted, as the temperature changed, it would push on the seismometer and tilt it a little bit. So they built a whole little tether, essentially a tension loop into the thing to make sure that wouldn't happen. And then when they released it, it didn't release as far as it was supposed to. So we'd put a little thing on the tether so we could actually take the arm out and pull it back a little bit. And that took about a week to go out and do that. But that was, again, one of those things you try to think of everything that could possibly go wrong and figure out, well, what are you going to do if that happens? All right. So this is our what they have found as far as seismic events. Some of these are Mars quakes. And there's kind of a couple interesting things. These colors, so each of these days, each stripe on this picture is one particular Mars day, which we call a sol. It's about 40 minutes longer than an Earth day. And essentially what this is showing is how much noise do we have at that time. And what we're finding is the atmosphere gets real active about sunrise, and then right at sunset, it just drops off and goes very quiet. So we're not actually getting much seismic data during the day, but we're learning a lot about how the atmosphere forms and how the winds form. But what they have found is a whole bunch of different seismic events that are going on, essentially, primarily during this kind of period from 6 p.m. to midnight, and that's when we're most able to sense things. One of the other things I heard our scientists say, Mars is generally very quiet. One of the interesting things about the Earth is the Earth hums. There's a seismic hum. And they say if you put a seismometer down even in the middle of the continent, even in Kansas, you can hear the ocean. Because there's kind of a hum from all the wind blowing and the waves crashing and all that type of thing. So they're saying they're actually detecting a lot smaller quakes, smaller events that on Earth they wouldn't be able to detect because they're masked by the noise. Anyway, so we're getting lots of seismic events. I'd have to leave it to the scientists as far as exactly what they're finding out from this, but they're getting the data we were looking for. And then the final thing we're working on, I hope this is apparent. So I talked about our mole, and the mole kind of went about a foot into the ground. There's about 4 inches of it sticking out of the ground, and it's not going anywhere. And it looks like what's happening is the soil of Mars is not quite as sticky as we thought it would be, and it's kind of probably hammering and then bouncing and hammering. We're kind of counting on that. So what they've been doing is they use this scoop to kind of push on the soil to see if we can compact it. That didn't quite work, and what they have done now is they've kind of pushed sideways on the mole to try to push it into the side of its hole. And in the last week or so, it's actually started moving again. So they did a couple of hammering, and it's moved maybe an inch or half an inch, but it looks like it's actually moving. So hopefully, over the next few months, we'll actually start getting that data. Okay. All right, and as I said, there's a Mars weather site, and you can go find out about being a Martian. Now, if somebody could help me, I want to move over to the other presentation. Can somebody give me a hand with that, or? Oh, I think this is it. Yeah, it's this one. You can go full screen. Okay, so what I want to do now is I want to talk about terrain relative navigation for Mars 2020. That essentially means figuring out where we are on the surface and navigating to where we aren't. Unfortunately, this isn't the area that I'm an expert on. Andy Johnson and Al Chen at JPL are. They're in the middle of getting ready for a review on this to get approval to fly it. So they briefed me. I hope I can understand it well enough to explain it. Okay, so kind of the big message here is the places that, so this is surface science, so they want to go look at rocks and layers and stuff like that. And the best places to go look at that are places where you don't want to land because it's not safe. All sorts of places where they have steep slopes and lots of rocks and lots of other stuff to look at. So the problem is, in order to get to the good stuff, the MSL lander landed at a spot that was safe and then spent the next 2 years driving to where the good stuff was. So this is a map of the Curiosity lander. This Mars 2020 lander is essentially a reflight of the Curiosity lander with a different instrument set. So Curiosity, landed up here. Where they wanted to go was, there's a big mountain, Mount Sharp, in the middle of the crater that we landed in. They want to drive up the crater and start looking at the different layers and strata and that type of thing. So we start here, and essentially we drive and drive and drive and drive until we get up in the foothills of the mountain and actually start driving up to where we wanted to go. And that takes about 2 years. It wouldn't necessarily take 2 years. The scientists like to stop and do science along the way. So, and so we found out a lot of interesting stuff along the way as we were doing that. But essentially, it says if we could have landed where we want to do science, we could have gotten to it immediately. So what they're trying to do on 2020, again, this is the same thing. Just overview of the mission, very similar to the Mars 2020 lander. One of the things, the Curiosity lander. One of the interesting things they're doing is, along the way, they're going to take a bunch of rock samples and put them in a cache, essentially a heap, or someplace. And sometime in the future, we're hoping to get a sample return mission that will go pick up these different interesting samples, bring them back to Earth so we can analyze them. That's not funded yet. This is a breakup of what Curiosity looks like coming through the surface of Mars. This is sort of analogous to the InSight. There's a cruise stage that supports everything as we're flying all the way out to Mars. There's the back shell, which has the parachute and protects us as we're going through the surface. There's the sky crane, or the descent stage. That's the thing that hovers and then lowers the rover down on a rope, a tether. And then this is our heat shield. Okay. So what happened on Curiosity when we landed, there's this process where we hit the atmosphere, it takes about 7.5 minutes to land. We come through, braking on the heat shield, parachute, drop the heat shield off. We have a radar that tells us how high we are above the surface. And once we come off the parachute, the radar tells us how high we are above the surface. We drop down to about 30 feet off the surface and then come down on this tether. So sort of what's important about this for this discussion about terrain relative navigation, when we reach the top of the atmosphere, our navigators know where we are relative to Mars within an accuracy of something like 3 kilometers. So 3 kilometers is like 2 miles, I think, if I do the math right. On InSight, the same number was about 5 kilometers. And that seems like a fairly big error, but from a couple 100 million miles away, that's not too bad. But it says that, and that's kind of the biggest contributor to our landing uncertainty. You know, if we don't know where we are at better than 3 kilometers, we can control very well, but we actually end up 3 kilometers away from where we thought we were. Okay, which means that they have to, again, as I said, we have to target to an area, you know, where we know it's safe to land anywhere within that 3 kilometer ellipse or something. Okay. So what they're trying to do with 2020 is make that better. And what they have done is they've put in a lander vision system, a camera and a bunch of processing electronics. So as they come down, so we're going through the same process of a parachute, heat shield, all that type of thing, radar, but we're also taking images as we come down. And what they've done is they've built up from this Mars Reconnaissance orbiter that I talked about, they've built up a map that the spacecraft carries on board of what the landing site looks like. And I think it's probably down on here. Let me see. Okay, they can figure out where the spacecraft is with respect to this map to about a 40-meter accuracy. And then there's a separate safe targets map where essentially they use that to correlate. All right, we know we came down, we have maybe a 3 kilometer position error. I can find where I am in that landing map, and now I know to much more accuracy to like 40 meters, where am I? And then the second, and all this is done with pictures that are taken from Mars orbit. And then the second thing they've done is they've put together a safe targets map. So it says, all right, once you have figured out where you are, you can control to get to the area you want to land in, where are the safe places to land within that area? And that's to a resolution of about 20 meters. So we can actually come down an area that's got some rocks and some flat stuff and some rocks and other things and be able to pick a much more precise area to land in. And all this happens in about 10 seconds as we're kind of coasting across the surface. Okay. This is a picture of the Jezero landing site. This is where we're going to be landing. And they want to land, I think, essentially at the base of these cliffs and start looking at stuff that has run off the cliffs. Okay. So what they've done is they've put together this lander vision system. And as I said, it will take pictures as we're coming down, correlate where we are with the map, and be able to divert and steer to a safe landing place. Okay. So there's about let's see if he's got the timing on here. There's about a 10-second process. We can start something like 4 kilometers up. We take a series of images, get down to, let me see, get rid of this initial position error of 3 kilometers, and eventually a whole series of images, and we get down eventually to where we know where we are to within something like 40 meters. And all this is happening, like I say, in about a 10-second period. There's something like 6 images that we're processing in that time. Okay. So what they did, and again, this is not, I'm not as familiar with this. There's a camera that's supplied by the same outfit in San Diego that put together the high-rise camera for the Mars Reconnaissance orbiter. They flew a descent imager camera that we had on the Curiosity. which although they didn't use it for this, there's some really neat pictures of the heat shield falling away and the ground coming up towards us and that type of thing. So same type of thing. There's a vision compute element, which consists of a computer, and I'll show in a second, and some FPGA processing, essentially to do all the vision processing and the map recognition and all that. And then this is talking to the set of flight software on the spacecraft that controls estimating where we are and controlling the rockets to steer where we're going and all that type of thing. So there's a whole systems engineering process to put together the cameras, the vision processing, the navigation, all that type of thing, and make that whole system fit together. Okay. So this is our camera from Malin Space Systems down in San Diego, and even though it's supposed to take pictures of Mars, you can use it to take pictures of people in your test setup. And again, these are the same people. They have been doing this for a bunch of different missions. So, okay. This is our vision compute electronics. If you like to look at pictures of electronic boards, there's a RAD 750 processor that is essentially taking all the input. Actually, go back. There is a programmable FPGA that is doing all the vision processing. So that's taking the vision map, taking the image that we're getting from the cameras, correlating those, and trying to figure out where we are in that image. One of the things when I asked them about this is what's the effect of lighting, and essentially we're going to be the Mars orbiter, when it comes over, always comes over at about 2:30 in the afternoon. We're landing at essentially 2:30 in the afternoon. So the lighting aspects are pretty much the same. This does all the processing, and then the RAD 750 combines that with information that we have from the gyro navigation. It figures out where we are and feeds that back to our control computer. All this is happening on the fly as we're plummeting towards Mars. Okay. Okay, this was a set of slides about course landmark matching. So we start here, we've got something like a 3-kilometer error in knowing where we are. Take a map image. I'm not sure what the normalization is. I'm not the vision processing expert, if somebody in here is. And then we take the images that they had put together from the Mars Reconnaissance orbiter, and try to match those to what we are seeing. Go through these. Match those to what we're seeing in the actual descent image, and essentially they will correlate at some point and say, all right, that's where we think. That's the adjustment that matches the map best, and that gives us our information about where we are. So that brings us down to something like a 40-meter error in knowing where we are as we're coming down. And there's find landmark. I have to admit, this is the part I'm not as familiar with. But there's another process that they go through with relatively coarse matching and then with relatively fine matching. One of the interesting things I know they have to do with this is coming as we're coming down on the parachute, so we're swinging back and forth. So one of the things they have to keep in mind is how we're moving, and that the camera is probably not actually directly pointed down, so there's a certain amount of image warping and that type of thing going on. And again, finally finding, where we are. This is a diagram of where the hardware is located on our spacecraft. So it may be a little bit hard to see. All this stuff down here is our rover. These are the wheels. This stuff up here is the sky crane, the thing that lowers us down. There's a camera mounted here down on the bottom so that it can see where we're going. There's a set of gyros, inertial measurement units up on the structure that we're using to navigate. And then there's a set of division control computer electronics is here inside the rover, where all the other electronics are. This is the rover upside down, so the camera is sticking out of the top here, our gyro electronics, and this is where the computer electronics are inside this big, huge box where all of our control electronics and radios and instruments and all that stuff is. Okay. One of the interesting tests they did was in our assembly facility. They've got a little target board with a picture of the crater, and so they're actually sitting in. Go back. Taking pictures with the camera looking down at the simulated image and actually verifying on the flight spacecraft with everything running, that whole environment, verifying that we can actually take pictures and recognize them. So that's about, I think, is about as close as we can get to doing it in the real thing. Okay. Now I didn't get to do this, but the guys who work on this get to go out in the desert and actually fly this stuff around over the desert to test it. So this was a helicopter test they did. The computer electronics are up here. The camera is down here, and these gyro electronics are down here. And what they do is they went out in the Mojave Desert and picked particular places that looked somewhat like what we're going to be landing on, and went out and flew around and actually tested. Could they map? Yeah, and they would swing it around. They've got a whole pattern they went through. Okay, so they had gone out and mapped a set of places, put the maps together, and then put them onto the computer electronics, and then they go out and fly around over the desert. And they put together essentially a flight pattern to go through to sample a lot of different terrain and to give them some feel for the type of swing and motion that they would expect to see on the parachute. So if I understand this correctly, this is the image that they had put together from the maps ahead of time. So this essentially would be like the map we put together from orbit. This is the images that the camera's actually taking as it's coming down, and the squares are places where it thinks it has found maps, but there's a legend down here, places where it's thrown out particular targets that it's looking for because it couldn't map them, and the green ones are the ones where those mean to be a pretty good match. We think we know where we are in the picture, and then I think you can see it a little bit better on the next one. What it has done is, I think for each of these areas, it's recognized I'm in this area. You know, I can match up my map in this area, but I'm this far off of where my navigation says I am. So essentially, it's correcting its position to figure out where it is. And this is where the 3 kilometer down to 40 meter correction is coming. All right. Again, same type of thing, and they tried this over a bunch of different terrain. Okay. So all that is, they're going through the reviews now to get permission to fly this, but my understanding is that they will plan on launching this in July, and we should hopefully see it landing on Mars. I'm not sure exactly when it lands, sometime towards the end of next year or start of 2021. Okay. And this is the guys who put this together. And they get to go out in the desert and fly on the helicopter and stuff like that. I know the previous test, they did this on Curiosity. I don't know if they're also doing this here, but they actually put it on the nose of, I think, an F-15. And one of the things, I don't think any of these guys fly with it, but one of the things they did is they actually go up and dive straight at the ground. To give you an idea of what it looks like coming down. So, okay. Anyway, that's all I had. Look for us next year. Thank you. As I was telling Neil before, I've got the best job in the world because I get to work with the guys who do this stuff and put stuff on Mars. So, yeah. All right.
Pretty cool, huh? All right, so I get to do proud dad for a second here.
Sure.
My son actually, as an intern on the lander that's going up on the 2020 rover that'll have a name here at some point, worked on, there's a collection arm or collection device at the end of the arm on the 2020 rover, and he was doing the inspections on that box. And so what they're going to do is they're going to go wander around Mars and pick up, there you go, that box right
Yeah, it's up
there.
up in this area.
Yeah, is it the black one up there somewhere?
Well, this is the arm.
The arm itself. Yeah, somewhere in this piece here. And they're going to wander around and they're going to do these caches of samples and stuff and just sort of leave it on the side of the road. Go back and get it later and whatnot.
Yeah.
So
and actually, just to follow, when you were talking about putting all the pieces together, if we ever get that working, That's going to be an amazing
Yeah.
system because we're putting this together. We're putting this particular cache that has all the stuff in it. And then we have a joint experiment, a joint mission with the Europeans, and we're going to land a lander that will have, I think, a European rover on it, so it has to land close to the cache. They have to drive over, pick it up. I think they put it into a rocket, a Mars ascent vehicle, I think we build, that launches into orbit, and the Europeans launch an orbiter that rendezvous with that return capsule and brings it back to Earth. So there's just a huge system.
So and what's so cool about this stuff is that, correct me if I'm wrong on this, I believe that JPL has a specific requirement that everything they do is a one-off. Like anytime that they get into something that's a production thing, it can't be a JPL. Is that?
More or less.
More or less?
It's more a guideline than a rule.
There you go, okay. So for those of you that met my son, again, the proud dad moment here, he has just accepted a full-time position at JPL. He will be starting in the spring after he finishes his master's degree, and it was a good day to have that happen. So.
Okay.
Sorry again? Say again?
Proud. Way to go.
There, way to go, Dad. Yeah, he came home that night. He said, "So how was your day?" And I said, "My son got a job at JPL." That's all I got to say. So, and what's so cool about this stuff, and whether it's Sandy, and we talked about this here a moment ago, these guys work so hard on sweating the details of it because you just can't mix metric and English together at the same time. And when it works, you can the amount of emotion that comes out. I mean, we all have that too for everything we do. I have it on things like MacTech Conference and whatnot, and everybody has this on all kinds of projects they're doing. Sal's got it. What's your name? I hate that exactly. And Adam, every time he puts a book out the door, it's like there's an emotional tie to it. And these guys, when it goes wrong big. And so it's really, really neat to see. So, anybody get any questions? Go for it.
After the sky crane disconnects, buggers off, where's it go?
It just flies off and crashes, essentially far enough away that it's not going to put the lander at risk. But it just
Littering the surface of Mars.
we are littering the surface. We've put a fair amount of junk down on the surface. We put down something like a dozen landers. The surface of Mars is about the land surface is about the same size as the surface of Earth, because they don't have ocean. So it's not like it doesn't look like the parking lot.
David.
Yeah, it's kind of related. What happens to the parachute? Is the atmosphere thick enough for it to get blown around, or is it pretty much once it's down?
I think what they generally see is they can see. I think in some of the pictures they can see it inflating, but it's got this back shell sitting on the end of it. So I don't think it's powerful enough that it can drag it around. And I think what happens eventually is it gets covered over with dust. So.
And the atmosphere's 1%.
Yeah.
Of what it is on Earth. And so it's just enough to cause trouble and not enough to help.
So just one quick story. If you saw The Martian, which is a great film, but even the guy who wrote it said, the storm that starts at the start, that doesn't happen. They get very high winds, but the atmospheric pressure is so low that when I asked our science investigator, he said, yeah, it's kind of like a gentle breeze. So it's not hurricane force winds. Yeah.
Now you mentioned, you said 10 seconds. Was that in the descent phase of it, where parachutes deployed, camera scanning, like you have like a few seconds to select the landing site and then put it down, or is that landing phase longer than that?
I think what is happening is they have a portion of it. The localization part is essentially on the parachute. So it's something like 10 seconds. We go through this whole thing where you come down on the parachute and they let the heat shield off, so now they can see the ground. There's something like 10 seconds they have to get that, and then they drop off. And I'm assuming, I think, they have 10 seconds to localize and essentially select a landing site. And then once they drop off, I think essentially they're coming down because they don't have much ability to fly around after that.
Crash landing, basically.
Controlled crash.
Following the stuff.
Yeah. Yeah.
Someone back here? Yes? Going? going? How about a welcome here for thank you, Sandy.